before I start this talk, I want to acknowledge the contribution from the ERC Interaction Laboratory team. Obviously, Ken Melville, the creator and founder of this group. Ben Reinemann, who was a PhD student in our group a few years back, who was instrumental in developing some of the technologies, the unmanned aerial technology programs that we've been running in the group ever since, and the current lab members that that took part in some of the work that I'll be presenting today: Nick Pizzo, Nick Statham, Laurent Gras, Stefan Deaton, and Theodore Wrestliska. So, based on the theme of this quarter AOS seminar, I decided to give a technology-centric talk today. So I'll be focusing on some of the tools and that we use to further our understanding of ARC interaction processes. And these are some of the observational tools that we use and that we've been developing are shown in those photos here. I'll try to also go over the motivation for why we ended up using those platforms, and I'll be focusing mostly on the autonomous vehicles that we've been developing over the last several years in that talk. All right, so let's get started. So the general, let's see here. All right. So our general goal in our group is to develop a better understanding of the coupling between the ocean and the atmosphere. And that includes the role of ARC interaction processes on upper ocean and some mesoscale dynamic. To do that, we use a combination of laboratory and in situ approach combined with theory and numerical modeling. The in situ approach is very important, to the group. We put a lot of emphasis into that. And this is here, showing an example of a wave glider deployed during one of our experiments. So this will be, again, a focus, of this talk is on the observational component of our group. Why do we care about this? The physical understanding of the processes occurring at the ARC interface has a direct impact on global scale weather and climate modeling, and that's why we need to parameterize those. And those processes are shown here as a schematic. There's a lot of things to cover. There's a lot of things happening when the ocean and the atmosphere interact. What I want you to really grasp, from this sketch is a broad range of scales that you have to be able to observe if you want to further your understanding of those processes. Thinking about going from wave breaking, generating small aerosol and sea spray, to larger wave, wave groupiness, upper ocean dynamic, obviously through wave breaking induced currents, generation of Langmuir circulation or mixing through Langmuir circulation, all the way down to some mesoscale, longer scale processes, 10 kilometers, 50 kilometers, 100 kilometer process. So all those processes are connected together, and the scales at which you have to resolve those, to resolve those processes is a challenge observationally. This is another way to look at it. This is from Bia's paper a couple of years ago, adapted from Shelton, looking at spatial and temporal scale of ocean atmospheric process. And I like this plot because it really puts some good numbers on what you're dealing with. On the surface wave side, which is in red here, you're looking at sub-seconds to hours, which correspond to millimeters to kilometer scale or tens of kilometer scale. And you have other processes at longer scale, but you have to keep in mind that those shorter processes will have and will affect the longer scale processes as well. So the way, and actually to illustrate this, again, we can start looking at wave current interaction. This is a topic that we've been very interested in our group for a number of years, and I think is a good example of this multi-scale problem. When wave interact with current at the frontal boundaries, this is an example here, picture taken right at the boundary of a front. It is warm on one side, this is shown over here, and cold on the other side. You have wave steepening occurring, and that can lead to the generation of enhanced braking. So we've done quite a bit of work over the years on this, trying to better understand this problem. We're still, looking at this with Theodore in our group and Nick Pizzo through some other problem. But this is, I think, a good depiction and a good example of the complexity and the scales, the range of scale that is involved here. So how do we tackle this? Well, we use, our tools, which are the theory, modeling, airborne sensing, in situ observation, and laboratory study. Obviously, those one are observational versus theory and modeling. And that's really, coming up with a science question and trying to resolve it, from every angle possible. Then we have the problem of the scales. So we use different observational tools as well. So in the lab, we use, for a very small scale, we use, typically the laboratory that enables us to look at very detailed fluid mechanics problem, if you'd like, in that case, for deep water breaking wave and sea spray generation. When you get to somewhat larger scale, in the meter to kilometer scales, we go in the field using research vessel, autonomous vehicle, like I'm going to be talking about, and other airborne assets to capture all those processes, surface kinematics, upper ocean process, mixing, et cetera, down to some mesoscale. This is measurement from an airborne sensors that we call the MAS that I've talked in past presentation. And here I'm looking at surface temperature across a very sharp front in the Gulf of Mexico. The brighter color is warm water. The darker color is colder water, and you have this very sharp front, changing, it's a step-like change of temperature that occurs, like at the northern edge of the loop current, and also showing those streaks. The waves are aligned in this direction here. I hope you can see my mouse. And these are actually surface signatures of those long-wave circulation, aligned with the wind and wave. So these are the kind of things we're looking at, and obviously it's important for the mesoscale and larger scale processes because those smaller scale processes will have an effect on those longer scale. So today I'll only be talking about a small component of our operation, which is really the observational autonomous component. So the way we tackle field program is, again, to try to attack it from every angle possible. Each platform will have some benefits, and I'll mention that in a second. So we use a combination of ship, platform, orbital product, and manned aircraft research. This is a project with NASA, and this is a typical aircraft that we use, as well as this array of autonomous vehicles. I'm not going to be talking about FLIP. There is actually a new version of the FLIP that is being developed, and project is spinned up now that's starting next year in France with Ifremer, CNRS, and CNES that the group is involved in, but I won't be talking about this. I won't be talking about ship-based measurements nor airborne measurement. I'm going to be really focusing on those autonomous vehicles. I'll start with the unmanned aerial vehicles. I'll give some motivation on how we transition from manned aircraft research to unmanned aerial vehicles, as well as surface vehicles. We have a fleet of wave gliders that we've been operating for a number of years now. They've been a very successful program, and covering some of the new platform, kind of like next generation platforms that we have been developing very recently and that are coming up to speed now. So starting with the airborne remote sensing, we have a long history in the group of collecting airborne remote sensing observation. And the motivation here is simple. The coupling of the atmospheric and oceanic boundary layers plays a crucial role in local and global flux of mass, momentum, and energy. And those fluxes are still poorly understood, especially in high wind and wave environment, which are conditions that are very difficult to collect data in. Aircraft are great. They're able to collect measurements at very small scale, at a range of scales, from very small spatial to longer scale. Because it can cover a very large area. They also have the ability to fly low, which is really important because this is really where things happen. So what we've been doing when we do flux measurement from an aircraft, we try to fly as low as 30 meters. And this is an example here. This is kind of like in the context of sea spray generation. We've done some work on this with Ken back in the days. But you take an instrumented aircraft. This is a Scripps Twin Otter. You have the ability to do soundings. Going kind of looking at the vertical evolution of in that case fluxes or spray concentration. And you can also do constant flight altitudes. You can do direct flux measurements. You measure the vertical velocity, you measure all the variables, and you can compute flux of those variables since you have those constant altitude flight. This is challenging. This is an example. I don't know if you see the. Oops. I don't know if you see the video well, but I was in the cockpit here, flying at 30 meters in 30 meters above the wave, or 20 to 30 meters above the wave in 40-knot wind, and there is, it's not a very comfortable flight, I would say. This was an experiment back in 2010, and these are great measurements. I won't go into details. I just want to show the kind of capability we used to use. But again, there is some risk associated with it. Very few aircraft can do that. To my knowledge, there is only one aircraft, the Scripps Twin Otters, that still do low-level flight. So a big challenge. And and when it comes to risk, you also have to factor in salt and sea spray generation. There's a classical example of a NOAA P3, very capable aircraft, losing 3 engines out of 4 during a flight in, granted in hurricane force wind conditions, but it was at 800 meters that they actually lost those 3 engines. So it was pretty high altitude. Which, from a science standpoint, I think it's interesting because it shows that sea salt aerosol of large diameter can get up to that altitude. But it also shows, some of the risk, associated with it, with those kind of flights. Locally, if they were able to fly into a rain cloud, wash up the engines by chance, and were able to restart the engine and safely got back to port. But this experience puts some drastic limit on what can be done with research aircraft following this incident. So because of the limitation, we started to transition to smaller, lighter, safer platform that can be deployed from research vessel. And that's when we started this US program. I mentioned Ben Reinemann was instrumental in developing those instruments that could fit into UAVs. Mentioned some papers here. I highly recommend for you to have a look at it if this is of interest. The platforms that we use, kind of our workhorse, is called a Scan Eagle. It's a heavily used platform by the military. There's about 2 to 3 kilogram payloads, up to 11 hours endurance. So it's a gas engine. It uses a pneumatic launch. This is the launcher here. And for the recovery system, we use a skyhook. So the benefit is that these are kind of hardware that can be installed fairly easily on a research vessel. The challenge here was to go from like an NCAR aircraft, instrument package to to squeeze it into this very, very small platform. And that's what Ben did. So the central to all the work that we did was a flux payload. And that's what I'm presenting here. Again, if you were interested into flux, you want to be able to measure the vertical velocity, the vertical transport. So, through the course of his PhD, we developed this 9-port turbulence gauge probe that measure winds and momentum flux, along with other flux when you combine it with other variable at the altitude of the aircraft. We added laser altimeters so that we have information about surface waves, humidity, temperature sensor, sea surface temperature, fast response, optical temperature sensors, and hygrometers, so we can get sensible and latent heat flux, again, coupled with a gauge probe. And all those instruments were carefully calibrated in, against state-of-the-art instrumentation. So as I mentioned, we want to have the in-situ measurements as low as we can from the aircraft, using those kind of payloads. What we do want, though, at the same time, is having another aircraft, and it's kind of like a standard flight configuration, flying at a higher altitude, with all the capability. And by that I'm thinking imaging payloads. These are like the first payload I'll be talking about is the imaging payload, which gives you information about the surface kinematic. It's equipped with visible and infrared cameras. So it will give you some information about ocean surface processes, wave kinematics, braking, any kind of SST front, or all the kind of processes occurring in the ocean that you can relate to some of the variability or signals that you see in the low-flying UAV at 30 meters. And we also have a radiometric payload to get some information about solar radiation. So, oops, I hope this is going to work. Let me try this again. All right. So this is a deployment that some of you in the audience participated in. It's called Equator Mix. It was on the Revel. It was one of our first deployment with the ScanEagle. Just to give you an idea of the kind of operation it entails, you put the ScanEagle on the launchers. Again, everything was designed in-house, capable of sustaining 50 Gs. I think on takeoff, it's typically 25 to 50 Gs. And that's it, you're in the air. So that's a huge benefit. The Equator Mix experiment was right in the middle of the Pacific Ocean studying the undercurrent there, right at the equator. So the second you take off, immediately you get, and collect data, and you fly, at various altitude. There was some earlier some 30-meter runs. This is a Revel here. And again, benefit is that you don't need a runway. It flies into a wire. This is a view from the aircraft. There's a little hook at the tip of a wing, whereas the aircraft gets caught. And that's what you'll see from the view of the aircraft. It's landing automatically. It is stressful for all the science team when the aircraft comes back, but we're fortunate to be very successful and conducted a large number of missions. So very, very reliable system. Let's see if I can do that. All right. So what do we measure? We can do continuous atmospheric profiling of the atmosphere and the marine atmospheric boundary layer. This is a lot better than balloon sounding. With a higher density, we can target areas that are of specific interest, for example. So this is an example of wind speed, wind direction, potential temperature, and water vapor concentration. And what makes those platforms, different is we can also do flux. And this is some example here of collecting flux, momentum flux here, latent heat flux, sensible heat flux, in a sounding configuration here, and that's going up, as well as during straight flight. And there was a lot of work done by Ben on this. It is important. I mean, what we're showing here is, you see difference, when you do crosswind and long wing legs, and this is this is something that is known. This is associated with atmospheric rolls. This is important because it pretty much implies that, typically when you're on a ship, you try to drive the ship into the wind to get less flow interference from the superstructure, and I'll talk about this a little later. But what it's telling you here is that if you're measuring flux going into the wind, you're actually not telling the whole story, because you're missing this crosswind component, associated with this crosswind signal associated with the atmospheric rolls. So that's pretty neat. You can start using those kind of platforms, what we did in larger programs. So we had this program with a number of collaborators from DoDs that wanted to see if we could use those instrumented, better instrumented airborne aircraft, UAVs, to see if we could improve environmental prediction by assimilating information from those unmanned aircraft real time instead of just using balloon sounding or whatever they traditionally use. So we did a short experiment, just over 5 days, but gives you an idea. We flew for 48 hours, which is quite remarkable, sampling the atmospheric boundary layer from 30 to 1500 meters right off the coast of Virginia Beach. So this is kind of like the idea. You have a ship. We fly. Right away. We can collect some data. We can combine this with ocean measurements. In that case, there was also electromagnetic propagation and all this thing going on. And working with Jim Doyle, NRL, who was running a COAMPS model with and without US data. In a nutshell, without getting into the detail here, what it shows is that there was significant improvement when you use US data, or significant improvement in short-term and mid-term predictability once you start using US data in those simulations. There's also the benefit of, if you run an adjunct, if you do sensitivity analysis, those kind of things can be relocated. If you realize that really you need some data right over there as opposed to right over here to improve your predictions, then you can just send the aircraft at this location and get the data that you need to get better forecasting capability. So now that this is like some of the things that we've done in the air. One of the again, we were very interested in collecting measurement really close to the surface. So very quickly, we got interested in unmanned surface vehicle. The benefit of those vehicles is obviously they're very, they have a very small footprint. They're very capable. So when Liquid Robotics started to develop this platform, this is something that became of great interest, especially with the potential retirement of fleet that was looming at the time. So before I get into the platform here, again, I want to do a bit of background. Why do we bother with unmanned surface vehicle when you can just use a ship? Ships are very capable, especially for remote work, but they are really not ideal if you want to do air-sea interaction observation correctly. And the simple reason for that is that the ship superstructure itself is so large that the flow around, both in the water and the air, around the ship is going to be contaminated by the ship itself. This is a challenge. A lot of people have been trying to handle this through numerical simulation and correction, but it's not really working well, or it's not just good enough. There are very few observations of the flow distortion around the ship, and what I wanted to show you is observation actually of platform waves that we conducted in the North Sea a few years back at the Kvitebjørn platform, which I think is relevant here. We're doing an experiment. We're focusing on phase-resolved observation of wind and waves. And we're using, among a lot of other things, a wind LiDAR. So typically a wind LiDAR is going to be pointing up, and you can get those wind profile. But what we did instead is to point it almost horizontally, like this, above the wave. So the platform is here. This is kind of like for scale. This is the size of a research vessel. But you have 4 beams coming out of the wind Doppler profiler. So typically, again, it goes up, and by processing the data carefully, we can actually still retrieve a wind profile using data at different range. And this is what I'm showing here. This is a scenario where the wind was, pretty strong, 16 meters per second and 140 meters height. So this is height, this is wind speed, wind profile. This is kind of like the standard log profile that you expect. What I'm showing here is a case where the wind is with the wind and the wind Doppler profilers are in the same direction. So you're pretty much sampling the wake, and that's what you see here. You would have expected to have the data lying on this curve here, more or less, but you see this drastic reduction in wind magnitude, like that extend pretty far away from the platform, up to 250 meters or more. And also affect the height. So in terms of, you can think of it as, as a scaling, like, for a 50-meter platform, it's about twice the height of the platform. Now, if you think about the way ships are going to be sampling atmospheric measurement, they're going to go into the wind, and that's the scenario here. So we have the chance to have this LiDAR in the same configuration, and what you're finding is that obviously it does a much better job, but nevertheless, we see influence, even when you're putting on, when you're pointing into the wind, the LiDAR instrument, because of the stagnation point that is going to be forming, ahead of the platform, you're going to have a reduction, a deceleration of the wind, if you like, that will lead to an underestimation of the wind speed of up to 10%, up to 150 meters away. So like, 3 or 4 times away from the platform, which is quite significant. So it gives you an idea, kind of like an order of scales of the things that you're dealing with for flow distortion around the ship. So now you can also use drifting buoys, and that's what I'm showing here. They're very capable. There's sweep buoys and wave buoys and AOS buoys and all kinds of things. But one of the challenge, and let me see if I can log this here. The challenge is that they're drifting, so they're going to have the natural tendency to collect into convergence zones. So those convergence zones, associated with some mesoscale features, are not necessarily going to be representative of what's going on in the entire area that you're trying to study. And this is an example here, a movie that was conducted from, oops, where is my mouse? Let's see here, okay. That was conducted in the Gulf of Mexico, where a bunch of drifters were released, and 124 of them, you see the scale, 10, 20 kilometer scale, and all of a sudden they get trapped into the mesoscale features. And I'll let it run just for a second, because ultimately all those drifters that were spread apart end up pretty much in an area. They're all stacked together of the size of a football field. So that gives you an idea of the importance of those convergence, and in those, like in interpreting at least the information that you collect from instrumented drifters. And obviously, moored buoys are crucial. And CDIB is a perfect example. There's a variety of flavors. They're great, but they're also limited to specific location, and they cannot follow a feature of interest, and cannot be deployed easily in deep water, or at least for a cheap price. So that's, because of all this, we started to get into those platforms. So these are the wave gliders. They're wave-powered autonomous vehicles. I'm not going to be going into details of the, the propulsion mechanism. I think everybody is familiar with those. I don't think people are used to seeing them in action. This was a movie that Laurent took from Flip during one of her experiments, when there was a crossing from the wave gliders. I mean, I think this movie is great in showing the kind of the kind of sea handling the wave glider is capable of. My work with wave gliders started back in 2013, so just a few years after the company was started. I was lucky enough to get access to data that were collected literally by chance of a near intersect between a wave gliders transiting to Australia with a Category 3 hurricane, and in analyzing the standard instrumentation package, we actually got some science out of it, and we're able to look at the ocean response to this tropical cyclone and compare it to LES modeling from Peter Sullivan and NCAR, which was great. And more importantly, it really gave us some confidence of the potential for this kind of technology to measure the interaction process, and in particular for extreme conditions. So following this work, and through multiple round of funding with ONR, we developed this fleet of wave gliders. So we have 4 wave gliders right now, two yellow SV2 wave gliders and 2 SV3. They are heavily instrumented, especially if you compare to to other groups. We do a lot of flux measurements here, sonic anemometer, static pressure, a lot of wave measurement, directional wave spectra, et cetera, and I'll show that in a second. But we also put a lot of emphasis on upper ocean measurements. So we have thermistor chains, either through a long 50-meter thermistor chain that's not exactly shown here, or with a profiler. So we have a profiling winch now that can lower a CTD package with dissolved oxygen and fluorescence down to 150 meters, as well as ADCP. So we have a downward looking, kind of like traditional 300 kilohertz ADCP, and an upward looking here, signature 1000, that gives us, that extends the velocity profile up to the surface, remembering that often from a ship, you're limited in what you can resolve close to the surface. So these are some examples. We're putting together, Laurent is putting together this summary paper where we go through all the kind of like the validation of all the measurements that we've been collecting from the wave gliders using state-of-the-art flip measurements. You can measure wind speed, U-star, atmospheric temperature, humidity, pressure, various profiles, at large depths, directional spectra as well. I mean, this is obviously surface wave, and wave breaking is very important to us. We put a lot of care into that. And again, current profile. As I mentioned earlier, and this is a comparison between satellite data, I think, and wave glider based measurements, which is really nice. I'll focus on this plot here because again, we have two ADCP, one pointing down from the surface, a longer range, so you get 2-3 meters resolution, and a much higher resolution one going up to the surface. So when you combine those two together, this is what you obtain. In that case, we have two wave gliders. So these are the black and the blue line. So this is a signature 1000 pointing up, and this part here is the ADCP pointing down. And the red line is data from the satellite that was close by. And you see for the deep water measurement, it looks really good. We have a very good agreement. But what is great, especially in the context of this renewed interest in some mesoscale processes and tying some of those in situ measurement to orbital or suborbital surface kinematics, that we hope to get in the future, kind of like bridging the gap between deep water measurement or deeper water measurements and near surface measurement is quite remarkable. There is a slight difference here, but that's associated with spatial variability. Knows that they're consistent both systems. Another showcase is looking at the deepening of the ocean surface boundary layers. Some stuff that Jerry had looked at several years ago from FLIP, but this is what we got from the wave glider. So I'm showing here the solar radiations. So obviously, this is the middle of the day here. The wind is picking up in the middle of the day, like kind of like early afternoon type thing. Surface wave. You can see that as the wind picks up, surface wave, like the energy level at the high frequency of this spectrogram is picking up. So it's it's getting higher, and you can see like starting to see a pronounced peak over here when you have sustained sustained wind for a period of time. And then you can look at the temperature profile. And I should point out that this is not in linear scale, but in log scale. So it goes from 30 centimeters down to 40 meters actually. And what you're seeing here is that you have the thin seam warm layers that is very difficult to capture. I mean, you see this is kind of like taking some slice at different time. This warm layer that you of up to close to a degree here that is created under the action of solar heating. But as wind picks up, you see this warm layer deepening down through direct and indirect mechanism, and by that I mean wave breaking. You're going to start getting micro breakers and actually aerated breaker, as well as enhanced mixing through Langmuir cells, which I think is pretty neat. We can capture signature of Langmuir in the T-chain data from the wave gliders, and this is shown here. This is another experiment. Flip was here. We did multiple transect with the aircraft, with an aircraft, and I'm not going to be talking about the aircraft too much. That's another talk by itself. But with the aircraft, we can collect surface imagery of infrared imagery of the ocean surface and look at the spatial structures, and we can capture, as I mentioned earlier, surface signature of internal wave. But what was really neat is that we had coincident flights we had coincident observation between the aircraft and the wave gliders, so that we could actually compare measurements and observation near the surface from the wave glider with the aircraft. And this is what you get here. I mean, qualitatively, you see those kind of cell-like structures in the temperature signal. These are the same data. I'm just saturating and changing the c-axis so that you can see those signature of Langmuir circulation a little better. And they're consistent with, and if you take a spectra of this, that's what I'm showing here in blue, so the data are really close to the surface, you can compare it with the spectra that you can obtain from aircraft data, and they match very, very nicely. And finally, like another example here, showcase the kind of capabilities that we have with wave gliders, is a front crossing. And here I'm showing the temperature profile. So this is about 3.6 kilometers. This is in the Gulf of Mexico, going a very sharp front. It took about 2.5 hours to go to do those 3.6 kilometers. And I want to highlight a couple of things. One, the incredible details that you have in the structure of the front, especially close to the surface. Should mention that the way that we're able to resolve such detail near the surface is because of logarithmic spacings for all the temperature node that we have, which is really important, and that's why we can resolve such detail, including right at the the frontal boundary here, as well as internal waves. You can see clearly here a nice propagating internal wave. All right, so this is what we have, and this is what we're working on now. Obviously there is some limitation with what I talked about for the Scan Eagles. It's a big operation, requires a crew of people, pilot, et cetera, et cetera. And for the wave gliders, they're great, but they're slow. You can only go up to 1 to 2 knots. And when you start looking at the time scale, especially for some mesoscale and frontal processes that I mentioned earlier, you need something that goes a lot faster, and that's what I'll be talking about in a second. So one new platform that we have been developing is taking this man aircraft airborne instrumentation package that I mentioned earlier. It's the LiDAR, infrared, visible camera package, and miniaturizing it and putting it into a heavy payload multi-copter router, so we can deploy it right from a ship, so we don't have to use a runway. And these are kind of data that we had collected in the surf zone to give you an idea of the kind of details that you can get in terms of the LiDAR topographies that this instrument is capable. This is a large multi-rotor aircraft, 1.6 meter diameter, so it's a beast, but it's also very capable. Because it's such a beast, we needed to come up with another way of operating it from a vessel. So it is designed to automatically take off and land from a ship, not using GPS position, but using a target. And that's what we showed earlier here. If you look right here, there's a little target. And what it does is that there is a camera, and with a little bit of Kalman filtering between the GPS position, if you'd like, and the information that you get by locking onto the target, it can actually land very safely on a moving platform, such as a bicer. I'm just moving forward here a little faster. This is a landing phase. Oops, let me see. While we're driving at 5 knots into an incredibly small space. So this is, we're very excited about this instrument, and we hope to deploy it in a large field program in June. Let me see here. The other way we're trying to expand those kind of capabilities, again, looking into faster vehicles. This is an issue for some mesoscale processes, the speed of the current autonomous vehicles. So what we have been developing is this rapid autonomous surface vehicle system for some mesoscale interaction research. It is a fast 5.5 meters diesel powered, like up to 10 knots for the speed, shorter endurance, but still, up to 7 to 10 days endurance unmanned vehicles. It is or will be heavily instrumented. It's still under construction, or at least the instrumentation hasn't been added to it, but it is equipped with a towed body. It's a hammerhead system with various instrumentation. We have radar system, we have camera, wind Doppler, profilers, arrays of sonic anemometers, ADCPs. It's an incredibly capable platform. We were hoping to receive it in July, then COVID hit, so we had some delays. But the fabrication of the bare-born, I guess, system was completed last week. So we're very excited about this. And these are some of the pictures to give you an idea. Some of the things are folded up. I mean, we even have an A-frame on it, just to give you an idea of the kind of capabilities that we can utilize from this platform. And there's always a lot of question about seakeeping with those kind of platform. So I'll just show you a video that was taken with a similar platform up in Alaska into a storm, and you might be able to see here you go. Right on the right here, you'll be able to see a Seaworker 5. So this is a platform that we use in severe weather, about 40-knot winds, stormy weather. And this is collected from an hydrographic vessel, actually, in operation. But I think in terms of seakeeping capability, if you look at the way the platform is handling the wave, I think it's quite remarkable and reassuring as far as I'm concerned. All right, on this, I think that's pretty much it. Again, this was a technically focused or technology-focused presentation. Obviously we do a lot of science, but just wanted to really spend some time this time around presenting you the tools that we're developing to develop better understanding of air-sea interaction processes. All right, well, thank you.
Awesome, thank you very much. We'll open it up for questions now, and I'm going to kick it off with potentially an uncomfortable question. And I may have missed this a little bit, but I was wondering if you could talk a little bit about a lot of the finances or like the economic, situation around a lot of these systems, especially as you compared, some of the aerial systems around like ship time, in the wake of a ship. There's obviously science advantages, but I have to imagine that there's also huge financial advantages to using these unmanned systems as opposed to ships or things such as that. So I was hoping you could talk a little bit about that.
Yeah, I mean, so it's not black or white. I mean, if you look at, because we use different, we're also doing, for example, in this picture you see a G5, and you can assume it's really expensive to use a G5 from NASA. An aircraft like this costs about $700 an hour, give or take. So which is cheap. For a G5, it will be actually for very special work with NASA, but it would be 5 times this, roughly, plus some of the things. A ship is going to cost you $40,000 to $50,000 a day. So when you look at those kind of technology, it's a lot cheaper. I mean, you buy the hardware beforehand, and there is benefit to it as compared to an aircraft. A wave glider will cost you non-instrumented 3 days of a large ship. Ultimately, like the cost is one thing, but the way we think of this is more like, ships or aircraft are kind of like the mothership. It's kind of like an aircraft carrier is projecting force. We're trying to project science. You have like the main ship where you can launch all those autonomous assets. and really expand your spatial coverage. You know, if you think about ship measurement, for example, it's really a single point measurement most of the time. You know, you'll be missing a lot of things. So if you, instead of going at sea in a very remote location, if you go there with a fleet of vehicles, both in the air and the water, then you can really get much better understanding of what's going on, or, you know, study the process that you're after.
Awesome, thank you.
Questions? I'm not seeing the, yeah.
Luc, this is Bill. Got a question.
Uh-huh.
So could you comment on the last large vehicle that you were talking about? So ultimately the question is, how do you get it on and off the ship if you presumably carry it out to station? I presume it doesn't drive itself to the location of the experiment, so you're going to have to basically put it in the water from the ship, and it's a non-trivial size. That's no small task.
So it's designed for this. It's actually specifically, it's, you know, originally those vehicles are designed for hydrographic surveys. So they are designed to be recovered from a research vessels using the support boat, you know, crane. So that's the typical operation. A lot of the operation that we intend to conduct initially will be towing this vehicle from the Beister, actually, into the location.
Sure. So I guess I know that I appreciate that they're intended to be deployed that way. For the most part, the ships are incredibly reluctant to use their cranes in other than very, very calm weather. And so, you know, it's just a real area of discussion with the ship operator.
Yeah, I mean, I agree. But, you know, there's a lot of things that ship operator didn't want to do for many years, and they're doing routinely now. And that's kind of the way I take this. I mean, it's 3 years ago through UNOLS, actually, I've been, you know, I started to push for making unmanned aircraft as standard features on research vessel, and right away, the RV Tech and all their ship people just, like, you know, pretty much told me it's impossible. Well, it's not the case anymore.
Sure.
I think it just takes time, but I think the natural evolution of ship operation will be, you know, will imply using a large fleet of unmanned vehicles of various flavor, and they'll have to adapt to it.
Yeah, thanks.
Any other questions?
Yeah, Luc, can you hear me this time?
Yeah.
Good, okay, the mic's working then. Sorry about that earlier.
I
had a question about the aerial surveys. If you're using something like that, I forget the name, but, you know, an airplane, like a fixed wing craft, as opposed to something that can hover, is there a way of measuring surface wave number? I'm just picturing you would need multiple points, right, to get the wave number vector. And I'm wondering if there's a way that, because this thing is so fast, there's a way to do that while flying.
So first up, you know, I should mention this is a scanning LiDAR. So, you know, you get a transect, but you're absolutely right. I mean, typically we compute directional spectra by flying in one direction, and then you can do a 2D spectra, et cetera, et cetera. But, you know, we're not, you know, the plan for the unmanned aircraft is not to be only hovering, because there is some benefit in hovering, because you can park yourself at the front, for example, at the frontal boundaries, and start looking at the kind of the evolution of a temperature front and all those things. But typically we'll be flying at very low speed. And low speed for us is good, you know, because the lower you go, though you have to deal with, you know, Doppler correction, because the wave field is going to be evolving in space and time. The slower you go, the higher the resolution is going to be. if that makes sense.
So if you're interested in wave number, you mentioned earlier you can fly a transect in one direction. So do you routinely fly multiple directions in order to get an idea of the wave number spectrum in all three directions, or both directions, I guess, in the plane?
So from the plane, if you fly high enough, you'll be able to get the directionality of the wave field within one direction. Okay. But if you're more interested in, like, I mean, typically what we do is to make sure that we can characterize the cross wave, direction. We do a cross, we do an upwind downwind leg, if you'd like, and a cross waves, kind of like in a cross. So we can ensure that we have enough directional resolution to do this.
Great, thank you.
You're welcome.
Unless there's any last questions, then we'll conclude it here. Last call. Okay, well, thank you very much for presenting today. This was absolutely awesome.
Well, you're very welcome.
I'm sure many of the students here are very excited about the autonomous vehicle propositions that you've presented. Again, that's part of one of the reasons why we had as our themes this quarter, is because I know we are all in particular very excited about it. So thanks everybody for coming. As always, just a final reminder to go ahead and sign up for the AOS seminar list, and we'll see you next week for our last seminar of 2020. Hopefully next year is a little kinder to the world.
Thanks, Luke.
All right, thank you. Thanks, everybody.